Hi, good morning, everyone. I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program. I have been very fortunate to conduct this what I call systems conversations with our distinguished speakers that we bring to Cornell to talk about their view and their research on complex systems. Today, we are very delighted and honored to have Sanaz Mostaghim, and she is a full professor of computer science at the chair of computational intelligence and the founder and head of Swarm Lab at the faculty of computer science at Otto Guericke University at Magdeburg, Germany. She holds a PhD degree in electrical engineering from the University of Paderborn, Germany. She is the vice president of the IEEE Computational Intelligence Society and the associate editor of IEEE Transactions on AI. Also associate editor on IEEE Transactions on Evolutionary Computation, and also member of the editorial board of several international journals of robotics and AI. Apparently, Sanaz, she is involved in so many diversified different areas and with unique contributions. So Sanaz, welcome to Cornell and welcome to our seminar series.
Thank you. My pleasure being here. Thank you so much.
Yes, I was reading, your CV, and also I was visiting your website. As I said earlier, I have been so amazed by the work you've done and also how your career evolved. And I am, and also I believe our audience, we are very interested in learning more about your career, your trajectory, and also your view about all these complex systems in terms of how they are related to your areas and to your expertise. Thank you.
Yes. Well, about myself and my career path, I did, as you said, I did my PhD in electrical engineering. I studied electrical engineering, and the time that I started my PhD, my supervisor told me, look, there is a new topic that you should work on, and it's called optimization, a multi-objective optimization. And I started actually my PhD on that and worked on optimization algorithms and multi-objective optimization, and they were quite new. So not so many people were working on these topics at that time. And actually I know them personally because at that time we were a very small community. And then I actually grew into this community, and I did my postdoc at ETH in Zurich, where I was applying the algorithms in geology and mineralogy. And after that, I started something in German system, we call it habilitation, which is a very complicated, sophisticated, let's say, version of a PhD, but it's more than that. So it's a qualification to be a professor, basically. Mm-hmm. And I did that at Karlsruhe Institute of Technology, was for a long time there. And actually from there, I visited Australia, I visited Yale University. Actually, I was a visiting scholar there just before coming to Magdeburg. And I did my habilitation degree there, and we work a lot on these algorithms, how we work with complex problems, how we can optimize them, how can we visualize their solutions, and various sort of problems. It was like applied computer science. So we were looking basically on problems. It doesn't matter where, in biology, mineralogy, chemistry, everywhere, logistics and so on. So there are problems that mathematicians, they cannot really provide us mathematical modelings for them. And we had simulations, and that was it. And the simulations were very expensive to evaluate the solutions. So we had to come up with efficient algorithms to find an optimal solution for this. And we were working on optimization algorithms, especially multi-objective optimization. And many people who I was working with, they were asking me, okay, so now you found many optimal alternatives, and now? So I started to think about, okay, after finding the several alternatives that we have to also work on decision-making. And decision-making is a very complicated task, even for human being. When you are confronted with decision-making, it means that it's a very uncomfortable situation. So you have to make a decision. You have to choose one out of many alternatives. In other words, you will lose the other alternatives that you have not taken. So it involves a lot of consequences and so on. So I was also thinking of how we can make a decision, how many individuals can make decisions. And yeah, so we were working actually on what you very well said, complex systems, and they are everywhere. And yeah, and lots of applications. And then I came to Magdeburg. And since I'm an electrical engineer, so I was always passionate about technical systems, and I had the chance to do that here. And I started a lab which is called Swarm Lab, and we established that. And my goal was not to have one autonomous system, but many of them, so fully autonomous. Like, imagine in future if you would have self-driving cars. They are all fully autonomous systems. All of them are complex, let's say, and they have to, work in one environment together. There are many things, many open questions for us in that area. And I focused on various aspects of that. And in my talk today, I'm going to talk about how they can make decisions on their own without the human intervention, and what challenges we have in algorithmic design and in system design, and all these aspects. So we are also working on this. And many people call it swarm intelligence because you have like many individuals. And once you have many individuals, even by human being, it's like that. Once you have many, then they emerge to some unpredictable behaviors. That so, for example, if you look at the election, one individual is voting for some certain person, but once you have a population, then something comes out that you cannot actually predict. And there are lots of local interactions in this. There are many sort of convincing issues in between. If so, you will see in my talk, I will talk about collective decision making, that the individuals, for example, whenever they get close to each other, they try to exchange information. So the communication topology is very interesting in that case. The network topology is very interesting and makes the problem very complex. And so we have this sort of emergent behavior coming out of a collective. And imagine if we have decisions to make in a collective way. As engineers, we are interested to know, we want to trace back, who has done what. And yeah, and we do a lot of research in that area as well, how we can have self-organized systems, how we can analyze that, and so on.
Wonderful. Thank you so much, Sanaz. So, when I was listening, to your introduction, basically I was trying to summarize. So basically, I think you talk about two levels. One level is kind of like technical research, like in the technical core of your research, like you develop advanced algorithms and models to help us to optimize. That's kind of what I call it, the technical level. And then also there is application level. I think you talk about another very important issue, which is decision making, whether it's individual decision making or it's collective decision making. It's very complicated. However, like your algorithm, your methodologies can be used to study either individual decision making or collective decision making, right? So I will try to follow that logic. I think it's kind of. I will try to start by asking questions more like specific at the technical level, and then we move on to a bigger picture that decision making. So in your while you are designing these algorithms and methodologies to optimize whatever question we are facing. So what are the technical challenges or barriers that you aim to break through in terms of optimization algorithms, especially when of course, I think optimization, like operational research as a field has been there, for a long time. However, I'm really excited about, like, when you look at, kind of multi-criteria kind of optimization or decision making. So what kind of challenge does multi-criteria or multi-objective optimization present to the algorithm designers like you?
Yeah, so multi-criteria decision making means that you do not only have one function to optimize, but you have several functions that you want to optimize them at the same time, and they are in conflict with each other. And this is the challenge. So you do not have, if you have, let's say, a set of solutions to the problem, if you would have had only one function to optimize, you could actually have a complete ordering of your alternatives. You could say, this is the best, this is the second best, the third best, and so on. So that would be a complete ordering. But once you have multi-criteria or multi-objective optimization, you cannot have any more complete ordering. You have a partial ordering. What does that mean? It means that the solution of this problem or solution of the multi-objective optimization problems is not anymore one solution, but is a set of optimal solutions. We call them Pareto optimal solutions. And there are many challenges. For example, one of the challenges is that you do not want to have, basically what you want to have is a good approximation of these Pareto optimal solutions. You want them, if you have, let's say, 10 solutions, you want these 10 solutions be exact optimal. So it means that they are exactly located on the Pareto frontier, what we call that. And we want also these 10 alternatives be well spread in a so-called objective space. So it means that we do not want to have all the alternatives if you would have had only 10, you don't want all 10 be very close to each other. You want them, they represent these alternatives or trade-offs in the best possible way. And since for many real-world applications, we do not know where the optimal solutions are, it's very difficult for us then to claim that they are well spread along the space. And we don't know where they are. We don't know if we have a solution in hand. We don't know if this is a real optimal solution, or maybe if you would have put more effort on that, maybe it would have been another one which would be better. And all these aspects. And this is the challenge in these problems. But these problems, the algorithms exist for quite a long time now, for about 2 decades. One on the top of that, what is challenging is, for example, if you would have had problems that the functions are changing over time, we call them dynamic problems. Or, for example, problems that the decision variables that we have, the number of variables increases to not only 10 or 20, but you are talking about 1,000 decision variables. Or the number of objective functions that you have. In my talk, you will see only 2, because with 2, you can visualize the trade-offs very well. But what happens if you would have had 4, 5? And how do you represent the solutions to the decision makers? How do you evaluate the quality of the algorithms? These are all the challenges that we have. And also, if you have engineering system, you want to have a robust, optimal solution, and not a solution that is not robust. So you are also interested in robustness and measuring how robust and reliable a certain solution is. So there is a lot of research questions in this area, and there's a huge community working on that. And yeah, maybe if you want, I would explain in one or other direction more into details.
That's wonderful. I think it's kind of, in your short answer, I think you already kind of brought up, several key aspects, which are so critical, in dealing with, optimization. And you are right. In the real world decision making, it's not really you have a single objective function that you want to optimize. Instead, you have multiple objectives. So, I think it's kind of the beauty of this multi-criteria optimization, especially when you think about, application. I feel somehow we researchers, we have some struggle, at the one level, because as engineers or even as computer scientists, we can dive into the details of this algorithm And we are, in the end, we are so excited. Yes, I solved this optimization problem. And then when you raise up your head and you look around, oh, actually, there is another higher mountain to climb. So kind of, I think technical-wise, technology-wise, we can use engineering and science to get to the extreme optimality. However, on a philosophical level, so kind of what's your view about, for example, exploration versus exploitation? Like you can exploit the algorithm to the optimum, and then in the meantime, you want to maintain some energy to also be able to explore such that you don't miss, for example, the global optimal. So, and also you talk about the solution space, or we call it architecture space, right? We can optimize architectures by focusing on some limited dimensions. But in the meantime, right, when you expand the dimensions, you see some other, all of a sudden, a new space for you to explore. So now I'm coming back. So what's your view, especially like in you're talking about large scale systems optimization. So how do you feel about this kind of balance between exploitation versus exploration in optimization?
Well, actually, exploration and exploitations, there are important operators that we have in optimization and in all sorts of optimization problems, not even, I mean, you can have also strategical games, and exploration, exploitation, they're the important factors that we should use to search for optimal solutions, actions, strategies, policies, or whatever we call them. So, well, there should be a very nice balance between them. I mean, if you only use exploitation, we usually say that we'll stop somewhere which is a local optimal. And you definitely need to have exploration. Then you can also go towards, you can search also other parts of the search space. So one thing basically is, I cannot say that is in all our problems or algorithms is an important factor, but most of the optimization algorithms, what they do is that you start with explorative behavior. So basically you start with random search, let's say. So more randomness in the first iterations. And the more you go over the iterations, optimization iterations, you change this proportion of exploration and exploitation, and you try to do more exploitation. So we hope that in the beginning, we hit somewhere close by this explorative behavior or exploration, we hit somewhere the global optimum, we at least hope that. And then with exploitation, we try to make it better and do the fine tuning to get there. This is the concept of many other algorithms that are actually, I mean, they are not really new. I mean, many of the optimization algorithms that we know, even the conjugate gradient or other approaches, they have this sort of learning rate, and you can actually play with that. In the beginning, you can have large steps, and at some point at the end, you can have smaller steps, which leads to exploitation. You can also have, for example, in a search for optimal strategies. For example, if you look at the problem, multi-bandit problem, where basically what is happening there, you start with exploration and then you try to change to exploitation. And exploration always helps. So sometimes it takes more energy and evaluation from us, because then we are spending time on probably randomness, nonsense, let's say. But if one of these randomness issues, random movements help us to get out of the local optima, it actually gives us a lot of benefits in searching for searching for optimal solutions.
That's great. Thank you, Sanaz. Thank you for the explanation, and I totally agree with you. I think from this point on, we are going to gradually migrate to, the second level, technical level, and then the decision, because that's another thing that you talk about. So when of course, you develop all these techniques, algorithm methodologies to help decision making, right? To help decision. So Sanaz, so when you apply your algorithm or your methodology, or when you use these methodologies to help the decision makings, of course, I guess there might be exciting times that your methodology, your results were adopted by the decision makers that generate the impact. There might also be times you might be frustrated, right? Your result, you offer all these insights, but they didn't listen to you. So kind of in this whole process, I'll start by asking a question. Is there, when we are moving to decision makings, is there an optimum? Should we pursue optimum, or like a kind of sub-optimum? So kind of what's the philosophy? What's the philosophy like you have learned in terms of kind of bridging our research methodology to the real world application?
Yeah. So once you have a multi-objective problem, the solution for this problem, as I said, is a set of alternatives from which you will select one. So there are two ways of solving such problems. One way is that you give the preferences of the decision maker before the optimization. You change this optimization from a multi-objective optimization to a single objective optimization. And the optimization is delivering the answer to the decision maker. And if the decision maker looks at the answer and says, oh no, this is not the alternative that I was looking for, so it changes its preferences and then gives it to you, and then you have to run the optimization again and then deliver him another solution. So this will go back and forth. This is called a priori optimization. Many classical algorithms, like from the time 1700 something, it goes back to this scalarization. So you change these many functions to one function and you optimize them. Uh-huh. The algorithms that I work with, they are different. We find a set of alternatives and they are optimal, so basically, or close to optimal. And then we give these to the decision maker. So that means that the decision maker is actually trusting us that we are giving the decision maker optimal alternatives. So one alternative is good in terms of one objective, the other one is good in terms of the other objective, and there are some in middle, but they're all so-called Pareto optimal.
Yes.
And then the question is how to select one of them. And this also depends. So at some point, many of us who do optimization, we stop with the work and say, okay, this is the set of optimal solutions. This we give it to the decision maker and we go home, let's say. No? In my research, I go one step further and say, okay, now I want to help the decision maker to decide and then we open a new research area, which is, okay, how to select. So of course, if it involves the human decision maker, then we have to decide if that decision maker has experience or doesn't have experience, if this is only one decision maker or there are many decision makers. So then for example, if there are many decision makers, so you can say, okay, I look at their preferences and I will deliver solutions which are the alternatives which are fair to all of them. So you measure the distances between the preferences and the solutions that you have. You also measure how much gain the decision makers have, and then you only deliver those alternatives. You don't need to deliver alternatives that are far away from all the decision makers, and so on. And then you can also have other decision maker like machines. Like I have like let's say self-driving car is standing in front of a roundabout and needs to make a decision, should I go or should I wait? And there are several conflicting objectives. And then we have to see how we can define a decision policy for that decision maker. So then we have to think, okay, how can we learn from the past? How can we gather the information, transfer the information from other individuals who have been in that situation before, for example, in the roundabout, and they had the same problem. So we have to then compare the existing problem with the problems in the past and see how close they are, the situations. And then we transfer the knowledge from one situation to the other, and we let the agents or the machines take the policies. Learning decision policy is very complicated. I had a lunch with a very famous professor, Roman Slovinsky, who is working on decision making all his life. And we had a lunch together, and I asked him, oh, okay, so you are so every time he gives a talk, very often his first example is, consider you are buying a car and you have several criteria. How would you solve this problem, and so on? So I was sitting next to him and I asked, Roman, you give this talk all the time about buying a car and you develop algorithms. I mean, he is academically older than me, much older than me. And I asked him, so have you ever bought a car based on your algorithms?
That's a great question.
He looked into my eyes and he said, no, my wife does that. So it is a difficult thing. I mean, the decision making itself, you can write algorithms and say, okay, what kind of solutions, what kind of strategies or policies you can have to make a good decision. But it also involves a lot of things from the environment, about the decision itself. If it is a one-step decision, like buying a car, it's only once. But if you have a decision that there are multiple steps, so you do not see the outcome of your decision immediately after you made the decision, but you see it like playing chess. When you play chess, you are making decisions one after the other. And then at the end, you will see if you won the game or not. No, so these are, and then the decisions are like how many decision makers are involved, how much information you have. So there's a whole science behind this decision making. But just going back to your question, in my research, we first find these optimal alternatives. So we think that all these alternatives that we have, they are optimal. And then we go one step ahead and say, okay, how we can select out of these optimal solutions.
Wonderful, wonderful. So, Sanaz, you asked a very good question to your senior colleague. I think so. I can see that, and you went through previously or traditionally, right? Decision makers are given, okay, you have this one objective function, you have this criteria, and then essentially the technical assistance or support like us, we can provide the decision maker with just one-dimensional objective value function, and then he or she can make a decision. But now, you made such a very nice kind of stride into this multi-criteria and this kind of Pareto front and this trade-off, which I believe makes the decision maker's life much harder, right? So they probably ask you, okay, why don't you give me just one dimension? Now, I want to move on to, so you already made a stride into, one decision maker faced with all these multiple dimensions or multiple criteria, which is already complicated. Now, if we move on to collective decision making, as you mentioned earlier, right? Now you can see that each stakeholder, they're facing multiple dimensions, and now you have these multiple stakeholders. So when you move from the individual decision-making to collective decision-making, what are the major challenges and possible solutions to that?
Yeah, so first of all, before I go towards that, I just want to tell you something, why I'm convinced that offering several alternatives is better than one only. I think it gives more confidence, even if you have one alternative that you want to take that. Once you have more options, even if you knew from the beginning that you are taking that one, still having more alternatives, it gives confidence to you that your choice is a good choice. So that's good to have many alternatives. We know it, for example, when we have medical treatments, we always want to have different opinions, even if we know what we want to do from the beginning. And there is also another point, but having too many alternatives is not good. So there is a law called Hicks Law that says that if you have more than 7, I think the number 7, if you have more than 7 alternatives, then people cannot make decisions. So this is one thing that I want to say based on your previous questions. But now for this question here, what I found out in my research, many things I found out, but one thing that I found out was, imagine that you have many machines, many robots, and we give them the ability to take decisions. So each one of these robots has the same amount of options that can be taken. They are in the same environment. And now we give them the ability to evolve or learn a decision policy. And what we realized was that they have some sort of human-like behavior. One of them turns to be very conservative. So among these, let's say, alternatives, let's say these are alternatives, how they move: fast, risky, close to the collisions, close to the obstacles, or how far from the obstacles. So, and all these aspects on movement. And what we realized that once they can make decisions on their own, and we do not see what's happening in their brains, but we can only see the policies that they learn, we realize that we do not have a homogeneous swarm or collective, but we have a whole spectrum of human-like behaviors. And that is because we just gave them the ability to take another alternative comparing to the others. So this is one behavior. And we also realized that communication is the most important part in collective decision-making, collective learning. What does that mean? It means those who are isolated because they do not have communication or because the environment is not giving them the ability to communicate with the others. For example, let's imagine those who are living in an island. They are not communicating with the others, so they learn to make decisions or take options or alternatives in a totally different way than those who move. And actually, we didn't need to give them any explicit given fitness, we call it fitness, that how they behave. We just gave them the ability to move. Once one person is moving, and is moving a lot, is communicating with more people. So it has a huge knowledge, let's say a table of knowledge or knowledge cluster that that person or that agent has. And in this way can make better decisions, can move better, can have less collisions, and is, let's say, very intelligent. And those who cannot move and have less communication, then they are less evolved and basically they fail. So it's very amazing, interesting research area where the communication topology is playing a huge role.
It does play a very significant role. So I think Sanaz, as our discussion or our conversation kind of moves deeper and also larger, I wanted to because when we were talking about that, and I was thinking to myself, because I think you're already kind of touching upon like a decision making by autonomous units, right? Or even some artificial intelligence, right? So now when I think more about it, for example, this algorithm, all these optimization technologies, including multi-criteria optimization, trade-off, all these things. All this, it's essentially provide us with more information that can support better intelligence, right? So now, my next question is really about like humans versus robotics or AIs, right? So imagine that provided with the same set of information. Of course, I think with all your optimization method and with all the visualization, whatever, or even communication, well, that all will provide information to support intelligence. So imagine that if we provide all this information to a human being versus to a robotics, who do you think can use the same information but make better decision?
It's a very good question. I don't know. This is I think I think the human being, the machines cannot still be better than human being. And I think there are several factors in there that the human being has this sort of, I don't want to call it consciousness, but this so-called integrated information that we are carrying with us. I mean, whenever I'm drinking a cup of coffee, I'm not thinking, the taste of the coffee. I could have a lot of very sophisticated sensors that exactly can tell you and me what is exactly in the coffee, where the human being might not be able to say that. But when I'm drinking a cup of coffee, a very special one, I might think of, the past experience, like how was it when I had a coffee in Austria or in Italy? So this whole integrated information that is in my brain is there. Now, coming to the decision-making, a decision-making that a human is doing is different, because this is a whole bunch of information that we have gathered over years and learned. And the machines that we have, you can also have many of them in many machines, but the technology of today is not even comparable to human intelligence at the moment, to my eyes. I cannot possibly say anything about their future because, the technology is improving so fast. But I think this amount of information that a human uses for making a decision is different. If a human being is making a better decision or not, I'm not sure, because we have very limited amount of knowledge for certain scenarios where machines can gather many information from many systems, analyze them faster. So imagine if you are in a situation, if I want to buy a car, I just ask my friend who had bought the car before and ask for his opinion. But a machine can actually do a very exhaustive search many servers, put many information together, and then the question is, if the machine is more intelligent, I would say no. The machine has more power to search. If I would have had that power to search, I would have been as good as the machine. So in terms of intelligence, I don't think that machines can be better than humans. I don't think that, and I don't think even in near future. But in terms of information processing capability, of course, a machine can have, can be connected to huge servers, get the information, be automated, search faster, and so on, where the human is not doing that in his brain. So, but one thing that we could do to deal with many machines, basically, why do we need to have these many machines? To make the life easier for us, for human being. And one thing that it's also an answer to your previous question, basically, I said the communication topology, but one thing we could do as human being, and I will show it in my talk, how to manipulate a collective of machines to make better decisions is to change their environment. So one thing we do is we work on the environment, and by changing the environment, because if you have many machines, you cannot go and change every single parameter of every machine. You can't. If you have 100 of them, the degree that you want to, this will be too complex for us to touch. But one thing we could do is that in order to control this self-organized system, one thing we could do is that we could control their environment. Imagine, we do it today, actually, many years ago. So imagine traffic outside, the cars, they are going, we are driving, and what they do to keep us as self-organized drivers, they put a traffic light. Traffic light is changing the environment for all of us, and once it's red, we all stop, and once it's green, it let us go. Imagine similar to this, we could do it for self-organized systems. Of course, not putting a traffic light, we could change the environment. We could change, for example, in an example in my talk, I will talk about collective perception. So a few robots moving in an environment, and they have to say what percentage or what color. There is a black and white chessboard environment. and they have to say which color is the majority. And for example, one thing we could do is that we could change the order of these tiles, black and white, using some isomorphic transformation. And then we can manipulate them to make faster decisions or better decisions. And yeah, so sort of environment of a collective is actually an important aspect.
That's wonderful, Sanaz. Thank you for clearing that. And I think you mentioned, I think these several layers. It's really, in the decision for humans, AI, and also decision making. First of all, there is information, and then there is intelligence, and then there is decision making. And I very much agree with you. I think machines, they can be very powerful in collecting and processing information, like at speed, probably faster than human brains. However, I agree with you. I guess machines, they have a glass ceiling for their intelligence, because human beings, right? The creativity. If we cannot kind of program the creativity for machines, they can never kind of surpass the human intelligence, right? I think that's the beauty of that. So now I'm just thinking out loudly. One is really, but you can see that decision making does not necessarily require superb intelligence. Right. So when I'm quite, yes.
Yes, it requires knowledge, but not intelligence.
That's right.
I'm also thinking loudly now with you.
Yes, please. Yeah.
Yeah. So I think the most important part of it is experience in making decisions. So experience means that you have to be in that. I mean, in the past, you should have had the same situation. And like playing chess, let's imagine chess is not 100% multi-criteria decision making, because chess is like every step of the chess, you are not trying to go back and forth. You want to go greedy approach. So you want to always win, because if you lose at one step, you will never end up later. So you go for a greedy approach. But imagine that we have a multi-step system. So we have to make decisions in a chain, a sequence of decisions.
Yes.
Okay. And I think the amount of information is important, and how we process that information. And at some point, if we do not have enough time, then we need to have a learning mechanism. Otherwise, you will have so much knowledge, and if you cannot process that knowledge, then and there are maybe situations that you do not have any entries for them. So it means that you really need to look at the data and extract the knowledge that you want to be able to cope with that decision. And therefore, learning is something, and therefore maybe intelligence is required. If we say learning is equal to intelligence, we could also debate on that. If someone learns something, it means equal that someone is intelligent enough or not. I don't know. I have no answer for that. I'm not an expert in that area, to be honest. I do a lot of machine learning, and I do a lot of swarm intelligence and AI and all these things, but still this is a topic that we can debate on that, and it's a very interesting topic. Yeah, but then if you have a lot of information, you have to process that information. And if you have to process, it means it's better to learn it than to process every time that we are in that situation.
Yeah, that's right. And I think that kind of learning can certainly, of course, learning with more abundant information, learning can certainly improve the intelligence level, right, of an entity. But I was just thinking, we collect information, we develop intelligence, and then we make a decision, right? So I'm thinking about the gap between intelligence and the decision for a human being versus for a robotics, a machine. One thing I think is kind of from intelligence to decision making, I feel the weakness of human beings is really like emotion sensation. These factors could be volatile. These factors, even the same level of intelligence, but because of the emotional level, because of the sensational, feelings, people could make either good or bad decisions. So, however, machines, they don't have emotions. They perform very consistently. So along this line, so let me ask you this question, like kind of facing our society's or world's great challenges. For example, this ongoing pandemic. Here again, I don't think there is kind of clear, true, right answer or wrong answer, but I just want to explore that with you. Let me ask this question: do you think, facing this kind of pandemic, would the world be a better place if we are governed by machines versus governed by human beings?
Oliver, that's a very good question. I don't know. This is a question that I cannot possibly give an answer. I don't know. So this is because this pandemic is something complex.
It is
very complex. I mean, I don't think that anyone would have an answer for this question, but this is a very good question. I didn't have such a good question for a long time, actually. This is what to the pandemic. I mean, we will know this definitely better, or we will know more after the pandemic is over, and we have done a lot of research on that to see, okay, what have we done correctly, what we have done wrong, and how we could do it better. And I think we really need to spend some research money on that. And actually, I have currently a project on that with my colleagues where we work. It's an international project where we work on these aspects. And we work actually on something which is called health and economy dilemma. So we do not only think about health of people, which is without any doubt an important issue, but we also think about economy, because economy has also impact on the health of people. So if people do not work, they will have mental health, and mental health is an important issue. So, and I mean, this is like a chain of things, and this is a dilemma. So economy, and that's why it's called health and economy dilemma. And we are looking at that actually as a multi-objective problem. And we have many research questions in that area than answers. Actually, we have no answer whatsoever to this. And I think that it requires research. And I think, so we need to spend some research money on this and see what happens, because latest, if we have that again in 100 years, a pandemic like this, hopefully in never, but if it comes, hopefully first in 100 years, still we have to provide answers to our, let's say, children in future, how we deal with that. And we have to tell them what kind of experience they should use to cope with such pandemic situations. Yeah.
Thank you, Sanaz. I think you mentioned a very good point earlier. You kind of answered my question. It's kind of, it's really, this pandemic as an example, it's a very complex, societal challenge we're facing. So actually, it's, of course, as a front runner, like in this area of research that you're working on. And also, when I was reading your website, I'm so excited because I feel it's really, this systems approach using multi-criteria trade-off kind of, techniques. I think this is really, I believe, one of the key approaches that can help us address a lot of, the key complex system challenges. Pandemic being one example, but even, of course, even think about climate change, and then also people talk about poverty and the food systems. It's interesting. While we're saying that, okay, the whole world, we are still facing some poverty problem. We are still lacking of food. But in the meantime, you see, in some places, like in the US, research shows that 30% of the produced food is actually wasted. So you can see that while a lot of people are working so hard on the supply side, okay, how can we make our agriculture to be more productive? But imagine that you need to invest probably, say, 10 or 15% more to increase the productivity by 5%. But you can do just make a little effort to save 10%. So that's again, all these kind of system challenges. That's why, I was asking whether machines can do better job or, human governance.
Yeah. For some governments, probably we could replace them by machines, and some governments I might not think so. I think it's a complicated question.
It is. But
machines cannot, I don't think. What I want to say probably at the end is that I believe that we should use machines to help us have better lives.
Yes.
And this was also the intention of engineers. We look at the Industrial Revolution that has been used to help us to have a better life, and not the other way around. And this is what I believe this is important, that we do not use machines in those areas that machines cannot be used. For example, where emotions are involved, where human emotion is involved, you cannot use a machine. There should be a human there.
Mm-hmm.
But many places, like in industry, we could use them. Fabrication, production, things like that. Agriculture, why not? Let's use the machines. But where the human being and the emotions and everything involved with the human intelligence should be there, I think we should use the human. The learning process, talking to people. Look, this conversation that we have, it wouldn't be as nice as this one that we have if I would have been talking to a machine, or you would have been talking to me as a machine, as my avatar talking to me. I think in certain areas you cannot replace the human being, and in some industrial applications, productions, fabrics, and so on, why not? Let's make the life of human being easier, and they then use their work time in some creative area, in some areas that we need human power, and having a better life. This is all what we do research for, right?
Yes. Thank you, Sanaz. Thank you for bringing us back. And I think, really, even though we're to the end, but I feel, those words you just said, actually, they brought out all these fundamentals. I feel, if I may summarize, I feel like what you said is essentially, we build machines, even intelligent machines, to help us live a better life. But human beings, we will live our own lives, and we will build our own better world.
Yes.
Yeah, I think that's it. Sanaz, it's really, I think today's conversation, it's be really kind of very, I think we went into the depths of the techniques, and also I think I feel really kind of excited, and also I feel rewarded from this conversation with you. It doesn't happen very often.
Happy to hear that. Thank you so much. It was really nice, and I didn't feel that it is taking 1 hour already. That's very nice. Thank you so much. I enjoyed it a lot.